All right, let's move on. You have something called the class here. This class explains a very important concept, which is something called 5B20 and something called 0.2 FS5. This is a very, very, very important part for me right now. And I forgot at the beginning of the paper, everything is white on white. So let's keep it that way. Now, engineers, we have something. He mentioned called 5B20 and another thing called 0.2 FS5. So what does this class mean? And what does the word class mean? The word class, engineer, here describes something related to the core, the ferromagnetic material, my iron core. All right, very good. So what does 5B20 mean? If you take 5B20 and break it down piece by piece, you'll find that the first thing, the 5, means that the accuracy of your steel accuracy, all right, it does not exceed, meaning it remains equal to or less than 5%. This means your ratio error does not exceed what? It does not exceed 5% when the current is up to, here's the idea, up to 20 times the current of what? The rated current. Where does this 20 come from? That's what it is. All right, this means your accuracy or ratio error will not exceed 5% as long as the current is up to, meaning as long as the primary current increases, it transforms into the secondary. The primary current increases, it transforms into the secondary, and the ratio error will never exceed 5% as long as you are less than 20 times the rated current. So, engineer, if I am now operating at a normal current, the full load current, well, according to the IEC engineer, which is the standard upon which this CT is based, the error ratio should not exceed 1%. This is at the rated current. That is, at the rated current, the average one-seed ratio error should not exceed 1%, while it follows the 5% rule as long as the current is greater than the rated and less than 20 times the rated. This doesn't mean it is exactly 5%. It will not exceed 5%. It might be 2%, 2.5%, 3%. Or it could remain at 1%, and that's not a problem. But as a manufacturer, I assure you that the ratio error will never exceed 5% before reaching 20 times the current. Okay. What's BADI mean? BADI means protection. It's simple. I immediately knew that 520 means it's a protection A core. So what does the 20 mean here? The 20 here has a meaning, one of which is the ALF, which stands for accuracy limit factor. This is the factor that determines the accuracy because the 20 means the factor or the number of times the current is determined at the accuracy level, which is written here as 5 or 3 or whatever the number is. The second thing, which is very important, is what? Do you remember? We said that the iron core is supposed to reach saturation at what? At what density? A high magnetic flux density. What is meant by this? Didn't we agree according to our circuit that we drew here, this one here? According to the circuit we drew here, as the current increases, it transforms and at the same time, it draws here until your core reaches the saturation stage, right? Okay, engineer, can you give me the equation for this circuit? Sure, I can get you the equation for it in seconds. The equation here says what, engineer? Let's see here, like this. What does the equation tell me? Well, the equation from this form tells me that the voltage, which is this, equals, if you neglect the secondary L here, it is the secondary current, right, multiplied by it. The secondary R plus the burden R, okay, which is the CTR plus the burden R, all right? Engineer, every time the primary changes, the secondary change increases. The primary change increases. The secondary change increases. The primary change increases. The secondary change increases until it reaches the saturation point. So where does it reach the saturation point? Here at the alpha. So LF here is like the accuracy factor that determines the accuracy for you here, meaning this accuracy is linked to 20 times the current. The same thing, what is it? And It means that I'm telling you my MCT to reach the saturation stage and the voltage on it to be the knee point. Voltage will reach at a number of times equal to whom? A number of times from whom? From the current equal to. And since I am a protection core, this factor tells me that in my manufacturing, I guarantee you that your CT to reach the saturation stage and the quality we look at will be the knee point voltage will reach at a number of times greater than the accuracy limit factor of I2, meaning at a number of times greater than 20 times the current of A from the current I2. But this is linked to the burden connected here, which is the rated A, the rated burden written on the nameplate of the current transformer. And 0.2 FS5, the same applies if you take 0.2 FS5 here, engineer. 0.2 means that my accuracy there is how much? It is 0.2%, meaning it does not exceed, or is 0.2% up to what? Up to 5 times also. What is my current? 5 times. Exactly. And what is FS? This FS is called the security factor. Okay, great. And what is the 5? It's the exact same idea. It determines your accuracy, plus the exact same equation that I want my CT to reach the saturation stage. This 5 is what is called FS, exactly in I secondary. In R's plus R burden, the idea here is that I want my CT to reach the saturation stage at a number of times of I secondary less than FS, less than 5 times. Less than 5 times. Why? Why, engineer? Because here I'm not protection. If I were protection, I would want it to reach at a number of times greater than 20.2 to leave room and prevent the system from saturating quickly. But here I want it to reach saturation quickly at a number of times less than 5 times. Why would someone ask why I want it to reach before 5 times? I would tell you because this is a metering coil. I am not required to measure high current values. And why is it called a security factor? So what's the idea behind calling it that? Like protection transformers. Protection transformers for whom, engineer? In the end, engineer, it's a transformer. What kind of transformer? A current transformer. And this current transformer is connected here to a meter device, right? Very good. So the idea here is that your meter device is supposed to be purchased with the understanding that it will measure currents up to a certain weight, correct? For example, up to 3 times the current, like a meter that reads 3 amperes, but its limit is 3 amperes, 3. So here, you are required for your CT to handle, for example, if your CT is rated at 1000 to 1, you want it to handle up to 5 times, meaning up to 5000, so that the current doesn't reach 5 amperes here. It might reach 4 or 3, keeping the ammeter safe. That's why they call it the security factor. Additionally, they call it the security factor for another reason, which is that the cross-sectional area of the cables of your current transformer winding is designed not to handle high currents at all, because it is assumed that the core should quickly reach saturation. And why? Because practically, I am not going to transfer these high currents. The meter is not interested in reading these high currents for my meter. Therefore, I don't need these high currents. That's why the cross-section of the winding is designed to be thin, as it carries small currents to reduce the cost for myself. That's why you'll find that the metering core is much cheaper, unlike the protection core, which is designed to handle 8 times, 10 times, or even 15 times the current. Therefore, the cross-section area of the conductor here is larger than the cross-section area of the conductor in the metering core. So here, you want the protection core to reach the saturation stage at a number of current multiples greater than 20, which is if it is connected to this. The rated burden is connected to this. And here, you want the CT to reach the saturation stage before, let's say, 5 times the current, which is the security factor of the current transformer, if also the rated burden is what's connected to the secondary circuit of the current transformer. Great, guys, very good. Okay, let me see. Where is my camera? I'm following. So this is my class, which is 5B20.2 FS5, and here I've written down its definition for you. I've also explained it in another video, which I'll show you, God willing. Great, guys, very nice. Next, we have something called I continuous thermal. The So this means, guys, the continuous RMS current, which is 120%, this means if your 60 is 400 to 1 or 1000 to 1, if 1 ampere flows in the secondary side, or 1.2 if it's 120% of the 1000 or 120% of the 400, depending on the ratio you've chosen, 1.2 amperes will flow in the secondary. Here, this means the continuous thermal current that will never exceed the maximum permissible temperature rise for the winding of the current transformer, so it won't affect the insulation of the current transformer. This is, of course, the standard that we will see tomorrow when we come to test, God willing. I will send you this standard. I have extracted it from the IEC because the full book, of course, costs money and is the company's right. So I have only extracted the part that you will need. As for sharing it with you here, the thermal here, this is the maximum RMS current. This is the maximum RMS current that can pass through the primary circuit of the current transformer. Consequently, it will be transferred to the secondary without any current flowing in the secondary, meaning the current that will flow will not affect or put the CT under thermal stress. But for how long is this applicable? For 1 second only, meaning just 1 second. More than that, and what could happen to your CT? It could be destroyed. Is that clear, everyone? So here, this is our nameplate, and this is, of course, the magnetization curve I mentioned to you. I told you that the primary part is linear. And I told you that every time the voltage increases by 10% beyond the saturation point, the excitation curve increases by 50%. The card is 50%. So this means the pre-saturation region, which is why it's called the knee point, the knee area. After that, it's not the saturation point. Rather, the system will reach the saturation phase. That's why I showed you and told you that this area here is unsaturated and the area above is the saturated point. So I told you if the load and the magnitude of the primary current are large, meaning the values of the currents are high. Streety point, footprint efforts, and the magnitude of primary current. All right, to cause saturation of the CT, neither the flux nor the induced voltage are sinusoidal, meaning there will be distortion in the voltage wave and also in the flux and consequently in the excitation current. You will have an error in the causes of the current, which will be large, due to the excitation current itself, which can take large magnitudes. This is what I explained to you when I told you the reason why there is a ratio error, meaning why the 1000 amperes are not converted to 1, why there is always an error. There is always an error, because part of this flux is used in the magnetization process of the iron core to align the dipoles. That's why during manufacturing, they don't make the CT exactly 1-to-1. Instead, they might add a turn to compensate for this error or to provide compensation. All right, guys, that's great. So it's also important to note that the knee point in the protection core is larger than the knee point in the metering core. Thank you.